So we're going to talk about something called Bayes' theorem, which is again going to be about conditional probabilities. So the way to kind of to tell you why this is useful is first let's look at a simple tree diagram. So imagine you've got some two-step procedure or experiment, or maybe I guess you just got two events maybe. So you have an event E which has probability 0.3. So the complement is probability 0.7. And then for whatever reason, if E occurs, then you know that the probability of F is 0.8. And if E doesn't occur, then the probability of F is 0.5. Okay. And you can come up with whatever scenario you want about this, right? Like, yeah, something happens with probability 0.3, like, I don't know, some sports team wins the game with this probability. If they win, then something else happens with some probability, whatever. Right, so from the tree diagram, if I asked you what is the probability of E, this should be super, super easy, right? Because if you understand what this diagram is saying, like this part just says the probability of E is 0.3. Okay, and if, for example, so basically I'm gonna tell you a few things that are easy to compute from the tree diagram. But then we're gonna compute something that's harder to compute. So can anyone tell me what the probability of F given E is from the diagram? Yeah? Yeah, exactly. So, right, because you're kind of, the idea is, again, you assume E already happened, and you say, if E has already occurred, what's the probability of F? And it's like, yeah, this branch of the tree. Okay, so this is, like I said, this is supposed to be easy information you can get from the tree. But here's something that's a bit harder. Like, for example, what is the probability of E given F? Okay, and that should not be obvious because there's no number in this tree that I can just read off immediately. It takes some work to compute this. So okay. So basically, that's the purpose of this Bayes' theorem. So Bayes' theorem, which I'll state in a second, gives us a formula to compute this probability of E given F using stuff that's in the tree. So using numbers you can find in the tree diagram. Okay, so maybe first what I'll do is I'll just state the theorem, which is just a formula you can memorize if you want to, but and then I'll justify why it's true. And so I'll state the theorem. We'll use it to actually solve this example, so you can see how it works, and then I'll tell you why it works. So it tells you that, so in general, the probability of E given F is equal to the probability of E. It's kind of a long formula. Probability of F given E on the numerator. Then the denominator is going to be, so we're actually going to start with the same thing as the numerator. So probability of E, probability of F given E. And then we add probability of E complement, probability of F given E complement. Okay, so in our example, so if you were doing some kind of test or something, if you remembered this formula and you wrote it down, you can now fill in all the different pieces, right? Because we know probability of E is 0.3, probability of F given E is 0.8 over, and you have the same thing again, right? Probability of E, probability of F given E. What are my last two numbers here? I want to multiply, yeah. Yeah, right, because we're going to do probability, this is the probability of E complement, right? And then this is the probability of F given E complement. So yeah, 0.7 times 0.5. Which, at the end, gives you approximately 0.40678. So this is definitely not something you can just look at the tree diagram and guess that it's about 0.40678. That wouldn't really be possible. So you really need this formula. Okay. Any questions about that example? Okay, we'll see more and more examples as we go. Let me justify why Bayes' theorem is correct. So this is the justification. So actually, like this formula might look kind of new, but there's nothing new in this formula. Like you can just derive this from things we've already learned about in conditional probability, right? So what's the original formula for the conditional probability? So it's probability of E intersect F over probability of F, right? But we also know that E intersect F, so if I look at, I'm just trying to break down the numerator, that's the same thing as, let the probability of E times the probability of F given E. Okay. So if I just plug this in for the numerator, we've already got the correct thing on the top of the fraction, right? So this, which I'll put a star, we can just substitute for the star here. Now let's do something about the denominator. So the probability of F, so the probability F occurs is the same thing as the probability that E and F both occur, plus the probability that F occurs and E doesn't occur. So this is a thing that has come up a few times now. Right? If you draw the Venn diagram, it kind of makes sense that F is the same thing as E intersect F and E prime intersect F, right? So the probability of F is the probability of this plus the probability of that, right? And then each of these can just be broken down in the same way as I did with this one. Well, I mean, literally, E intersect F is the same as what I've got here, so you can break that down the same way. And then this can also be broken down similarly as probability of E complement, probability of F given E complement. Again, if I call this happy face, maybe, you know, if you substitute this in for there, you get the formula, right? Any questions about that? So by the way, if this is not clear to you, that's kind of okay. You're never going to be asked to justify Bayes' theorem on a test. You really just need to know how to use it. But I guess it's not, you know, this kind of derivation can actually help you remember the formula, because you know, if you remember why it's true, you might also remember that it is true. But yeah, like I said, you can just, if you want to memorize this, that's totally fine as well. Okay. I feel like by saying that the test marks aren't so good, I put everybody in a, or maybe it's just a very dull, cold day, isn't it? Maybe everyone's a little bit sleepy or something, or too much turkey over the weekend. Okay, let's do another example. So let's say each day Nicole wakes up before 7 a.m. with probability 0.3. If she wakes up before 7 a.m., she has a 0.2 probability of having an afternoon nap. Otherwise, like if she wakes up after 7 a.m., she has only a 0.05 chance of having an afternoon nap. So what we're going to be computing is what is the probability that she woke up before 7 a.m. given that she had an afternoon nap. I'll just say had a nap. Okay. So if it's helpful to you, you could start by drawing a tree diagram. We don't really need to, because we can just kind of read off the numbers from the example and plug them into the formula. So maybe I'll go that way. So let's say that E is the event woke up before 7, and F is the event had a nap. So if we want to get probability of E given F using Bayes' theorem, okay, well, it's going to be kind of tricky to do this. Kind of covered up the theorem. Maybe I'll quickly write it here. Well, I'll just write it here. So what Bayes' theorem says is that's the probability of E times probability of F given E over, start with the same thing, probability of E, probability of F given E, and then add probability of E complement times probability of F given E complement. Okay, so all right, so what should I plug in for probability of E? 0.3, right? Probability of F given E? Yeah, so that's going to be 0.2 because we're saying, so probability of E is probability she wakes up early, 0.3, right? Probability of F given E is the probability she has a nap on days when she wakes up early, right? So this is probability she has a nap on a day she wakes up early, where early I mean before 7 a.m. Because it's the probability that F occurs given that E occurs. So it's assuming E occurs. Okay, and we've got the same thing here, 0.3 times 0.2. What about my last two numbers? Yeah. Exactly, yeah. Probability E doesn't occur, which is 0.7. And then we know that if she wakes up sufficiently late, like after 7 a.m., she's only got a 5% chance of having a nap. And then at the end of the day, you get something which is approximately 0.63158. Okay. So if somebody told you, if she told you that she had a nap today, and you wanted to know, okay, given that information, now that I've learned this, what's the probability she woke up before 7 a.m.? You'd say there's about a 63% chance, give or take, that she woke up before 7 a.m., given that she had a nap. Questions about that? So one thing to notice about these examples is we were always dealing with kind of binary events, like she either, there's only two possibilities. She either woke up early or didn't, and then, nap or didn't, right? But remember our tree diagrams, we could have more complicated tree diagrams, right? Where, at every stage there could be multiple different outcomes, right? So there is a Bayes theorem that works in cases where you have multiple different outcomes. So, so let's say for 3 events, for example, so you also have to know this version of Bayes' theorem. So suppose that E1, E2, and E3 are mutually exclusive. Events such that E1 union E2 union E3 is the whole sample space. So this is, this is very jargony, right? To kind of take the jargon out of this, like, what this is really saying is that exactly one of E1, E2, or E3 always occurs. Like, you can't have 2 of them occurring at the same time, and you can't have a situation where none of them occurs. So it's kind of like if you play a sports match or something, either it will be a win, a loss, or a tie. There's no 4th possibility. Or maybe, yeah, maybe it could be canceled or something. But yeah, no 4th possibility, let's say. So then, for any event F, the probability of, let's say, E1 given F is probability of E1, probability of F, over probability of, F given E1, probability of E1, probability of F given E1, and then the same thing for the others, probability of E2, probability of F given E2, and then probability of E3, probability of F given E3. Okay. So the situation where this would be, useful, right, is if you're given some kind of tree diagram like this, where you've got 3 outcomes at the first step, and then after that, F could occur, you know, in all the different possibilities or something, then the numbers on these branches can give you the numbers to put in the formula. So let's do an example using this multiple event formula. By the way, if you had 4 events, what would you do? It'd be pretty much the same, right? You'd just have the same formula here, but this would go from 1, 2, 3, and 4 if you had 4 different events on the denominator. Okay. So an office, let's say, has 3 printers, printer A, B, and C. Whenever you hit print, so when an employee prints, what happens is, for some reason, they can't select the printer. It just goes to a random printer, okay, with some weird probabilities. So, so it is sent to printer A with probability 0.25, B with probability 0.35, and then C with probability 0.4. Okay, these printers are not perfect. They can make mistakes. So printer A makes a mistake with probability 1%, so 0.01. B with probability 0.009 is the mistake probability. And C makes a mistake with probability 0.003. Okay. Okay, so now suppose that suppose somebody just printed and somebody brought it back to their office and it had a mistake. So suppose someone printed, so they just printed something and it came back with a mistake. So what is the probability that it came out of printer B? So let me let A be the event that it came from printer A, same with B and C, right? And let's say we let M be the event that it has a mistake. So from the statement of the question, what are we being asked to compute in terms of events and probabilities? Yeah. Yeah. Right, so this is what we're being asked for, right? Because it's saying, whenever you're doing this conditional probability, right, whatever you put to the right side of the line is what you're assuming already. So here we're assuming we already have the information that there's a mistake. And then it's saying, given that you already know that, so given that M has already occurred, what's the probability that B has also occurred? That's really what conditional probability is saying. So it's important to get that straight, right? That this is B given M. So M given B would be a totally different thing. Okay. One thing to sort of notice here is, like, these events do satisfy the criteria, right? You know, A, B, and C are mutually exclusive because when I send it to a printer, it doesn't ever send it to two of them at the same time, right? So mutually exclusive, right, means that A intersect B is empty, A intersect C is empty, B intersect C is empty. And also A union B union C is the whole sample space. Okay. I'm mostly just going through this because I'm trying to remind you what mutually exclusive means and stuff like that. When you're doing a problem like this, you don't necessarily have to write all this stuff in your solution. But it is important, like when you hit print, that job goes to exactly one printer. It doesn't go to two of them. It never goes to 0 of them. It goes to A or B or C, and no combination, not two of them, right? So that means we're allowed to apply this formula. Okay, so we've got probability of B, probability of M given B, over probability of A, probability of M given A, probability of B, probability of M given B, probability of C, probability of M given C. Okay. Okay. Once you've had a bit of practice with this should be really quick to write down. You should, on the top you just write, you take the event that you're interested in, you go B and then M given B. On the bottom, you just go through all three kind of events and write the same sort of thing, right? Okay, so we plug in numbers now. probability of B is supposed to be 35%, right? And whenever you print from B, it has a 0.009 chance of being bad. We've got 0.25 for A, 0.01 chance of being bad. We've got this. And then 40% of the time it goes to C, and C is pretty accurate. It's like a 0.003% chance of being bad. Okay. At the end of the day, you get something which is approximately 46%-ish, right? So it's 0.45985, right? So actually, if you get an error, there's a pretty good chance it came from B. So one thing is, what if I also asked you, so what if I also asked you for the probability of A given M? So you could go through the whole, the same whole calculation if you wanted to, but if you think about it, it's almost the same thing as this, right? Like the denominator is exactly the same as in the other calculation. The only difference is the numerator. So this is the same. The formula for this is the same as the formula for this, except the numerator is this instead of this, right? So if you think about it, probability of A given M is the same as, if I take probability of B given M times my new numerator over the old one. Which maybe is slightly faster to calculate, but okay, I admit that it's not that fast. But that's going to give you about 0.36496. Okay, and if you want to check yourself, the probability of C given M is going to be about 0.17518. Any questions about any of this? Okay. So yeah, this is really just a formula to memorize and get good at. Okay, so if there's no questions, then we can end like 10 minutes early or whatever it is.